Okay, thanks, Jan. First of all, I would like to thank the organizers for inviting me here and to everyone for coming to this talk. I'm gonna give you a kind of overview of something that you might not have been aware existed, and that is what I call parameterized proof complexity. So various co-authors and myself, we introduced this some time ago. The conference version appeared in 2007, and since then a number of other people made contributions to the area. And so I should say that this is not meant to be a comprehensive survey on the topic. So if you contributed something and it's not there, well, it means that I didn't like it for some reasons. It doesn't mean it's not good or it's not important. It simply means I didn't like it.
And it's personal.
Well, you will see some formal definitions and theorems, but I will start very quickly just to give you an idea. Well, what do we have in classical, traditional proof complexity? We want to prove certain propositional tautologies, and well, as Nicola pointed out, it's not always the case that the number of variables is the right measure. As the size of the tautology that we want to prove may be exponential in the number of variables. But in what follows, I will always use the number of propositional variables, the total number of variables, as a measure, and I will usually call this n. Whatever tautology I build upon those variables will be polynomial in n. And therefore, what I call the easy case or short proofs, these are proofs that are polynomial in n. Now it's a bit questionable as to what I should call hard proofs, and here I put fully exponential in n, although people might argue that, say, 2 to the square root of n is also a big proof, and it is certainly the case. Well, less obvious things that, like 2 to the polylog, well, you may put it as easy as hard, but I here make the distinction between polynomial and, say, fully exponential. And notice that the hard case, we have a trivial hard proof by simply examining all possible truth assignments. Well, what do we do to parameterize it? Again, we have a tautology, and the number of variables is the measure. But now we have some additional number k, which is a parameter. And it makes sense to consider natural parameters. This is something which is not well defined, and it will become clear as the talk goes. Well, it's going to be natural in the sense that the trivial proof would be of size n to the k. And then the easy proof would be of size polynomial in n, where the degree of that polynomial doesn't depend on k, times a factor which depends only on k. And that factor could be anything. Exponential in k, double exponential in k, whatever. Well, if you know what parameterized complexity is, you recognize this straight away. If you don't, well, think of something that I try to prove or refute for every possible subset of a set of n items. In the classical case, I will have to go through all of them. The trivial proof that would give me 2 to the n. If I'm clever, I can do it perhaps in polynomial size. If I restrict myself to the subsets of size k only, or size at most k, well, the trivial one, examining all these subsets, will give me n choose k, which is the same as n to the k. And the clever one is what is called as fixed parameter bounded. So now it's quite important at this point, if you have no experience in parameterized complexity, to think of the parameter as something which is not a constant, which is independent from the input size n, but which is much smaller than n. And from this point,
Why necessarily smaller than n?
sorry, D?
Why necessarily smaller than n?
In principle, it could be anything, but it makes sense to consider small parameters somehow.
No, bigger than 2 to the n, I agree, but there's lots of room in between.
Well, anyway, you will see examples, and you will realize that is what makes sense, at least in the context of these examples. And we will see that some of the results or conjectures or open problems that I'm going to suggest will become trivial as long as k is, say, linear in n, half n or something like that. So it really makes sense to consider small values of the parameter. Well, I don't think we have seen the Cook-Recco definition of a proof system. So we will see that definition in the parameterized setting. Well, for a moment, ignore the blue stuff in the first definition over there, and you get the classical Cook-Recco definition of an abstract proof system. We have some class of tautologies which are encoded over as strings over some finite alphabet. A proof system then is a polynomial time computable function that takes a tautology, that takes a proof and returns a tautology. So the meaning is a proof should be efficiently verifiable. Therefore, it's a polynomial time computable function. It looks at the proof and tells you what tautology this is a proof of. Well, now if you add the blue stuff, except for the apart from the tautology, you have something else which is the domain of all parameters. And in this case, the proof system will take a proof, tell you what the tautology is, and tell you what the parameter is. That's the only difference. So this is a minor amendment of the original definition made just to incorporate the parameter, nothing more. In classical case, we have the notion of polynomial bounded proof system, and that is a proof system for a class of tautologies for which every tautology in that class has a proof whose size is bounded in the size of the tautology. But in this case, again, it's an amendment of that definition in the most straightforward way. We require that every tautology has a proof of size polynomial in the input size times that factor that depends on the parameter only. So again, people who are familiar with parameterized complexity will see nothing strange here. Just minor amendments of well-known definitions in the classical sense, in the classical setup. A quick review or an overview of the fixed parameter tractability and parameterized complexity. A parameterized decision problem has two parts, the input and the parameter. It is tractable, again, if it's solvable in time polynomial in the size of the input times any function of the parameter only. And that is, it is now clear how the running time from a fixed parameter tractable fixed parameter algorithm corresponds to a short proof in the context of parameterized complexity. Parameterized reduction, I'm not actually sure if we ever need that, but it's a reduction from an input and a parameter so that you get a new input and a new parameter. The new input is fixed parameter bounded in terms of the old input and the parameter, and the new parameter depends only on the old parameter, but not on the input. You could ignore that if you didn't know it and didn't understand it, because it's irrelevant really. And I only needed that in order to define weighted satisfiability, in particular satisfiability for a formula in conjunctive normal form. So we have a formula in CNF and a number k, and the question that we ask, is there a satisfying assignment of weight k? Weight in this context meaning the maximal number of variables that could be set to true. And this is somewhat a natural parameterized problem. You only need to run through all possible subsets of size up to k and check for each such subset if satisfies the formula or not. There is something called W hierarchy, which starts with the class of decision problems that are tractable in this sense, fixed parameter tractable. At some point there is something called W2, and that is the class for which the weighted CNF satisfiability is complete under parameterized reduction. So W2 again consists of all formulae in CNF, a conjunction of unbounded disjunctions, and that's quite important. And we are asking for a satisfying assignment of weight at most k. W1 is the same thing, except that the disjunctions are bounded, so it's weighted 3 CNF, say. And for some technical reasons that will become apparent, it's convenient to work with W2. In fact, we don't, well, at least I don't quite know how to work with W1 in the context of proof complexity. A trivial observation that I put as a proposition: if W2 coincides with FPT, then there is a fixed parameter bounded proof system that would work for all weighted CNF contradictions. You would simply run the FPT algorithm that solves weighted CNF satisfiability, and the transcript of that on negative instances, say on contradictions, will constitute a refutation. Because it's fixed parameter tractable, the time is bounded, so it can only produce a fixed parameter bounded witness. So that is the sort of big motivation, if you wish, we have now. If we manage to show that there is no fixed parameter bounded proof system, we would separate FPT and W2. Well, as you may imagine, this is a fine, big motivation and, well, ambitious goal, but it is not quite doable, perhaps. So instead, we concentrate on perhaps weaker proof systems, trying to show that systems like resolution and likes aren't fixed parameter bounded in general. So first of all, I'll start with what I call a generic parameterization of a set of clauses or formulae in conjunctive normal form. And that is the parameterization that we had on the previous slide by the weight of potential satisfying assignments. And so if you think about it for a very short while, you will perhaps figure out that there are different ways to encode that parameterization. The most naive, perhaps, which I call naive, is to add many extra axioms for every subset of the variables of size k plus 1, to add a disjunction of negations. And it is obvious that that gives you the right parameterization. It wouldn't allow for any assignments of weight k plus 1 and bigger. But it has a problem, because if you add all these extra axioms, you get a very big tautology or contradiction of size n to the k. And if you measure the size of the proofs in terms of that, well, everything is easy, but everything is pointless. So to fix that, perhaps an actual refutation doesn't make use of all these extra axioms. And we will count only the ones that are actually used. So still n will be the input size, k will be the parameter, and we will count the clauses of the original formula plus the extra axioms, but only those that actually have been used by the refutation. The second parameterization, which someone called embedded for some reasons, is perhaps more elegant. It maps all variables that are set to true surjectively into a set of size k. And obviously that would constitute a contradiction if there were more than k variables set to true. But that has the disadvantage of adding some extra variables. And those extra variables encode the map from the variables that have been set to true to that set of size k. And if you have, well, most people have experience with proof complexity. As soon as you start adding extra variables, then you make it easier to prove or refute the original tautology or contradiction. And indeed, this is the case, as we will see later on. But it has the advantage that there is no blow-up in the size of the tautology. Everything that we add is of size polynomial in n and k. Well, to motivate the first ever result that we produced after we gave all these definitions, we will look at what is called a complexity gap for tree-like resolution. And that is a result that could be attributed to a number of people, but Søren Ries was the first who actually wrote nice and self-contained proof and coined the name complexity gap. And this is something, you may or may not share my opinion, but it is something which is really nice. Even though it talks about a very weak proof system, tree-like resolution, it's a result that gives you a lower bound for a very large class of propositional contradictions, not just for a single contradiction. What is it? We will only consider propositional contradictions that can be obtained by translating a first-order formula. And if you think about obvious propositional tautologies or contradictions like the pigeonhole principle or the least number principle. So the pigeonhole principle is there is no surjective map from n plus 1 to n, or the least number principle, total order or partial order over a finite set has to have a minimal element. All these can be expressed as first-order formulae. And so there is a uniform way of converting any first-order formula into a set of propositional formulae. And that is the most obvious thing that you could do. Replace all the universal quantifiers by conjunctions, the existential quantifiers by disjunctions. For every relational symbol, introduce a propositional variable, and so on. Introduce Schooling variables to flatten the formula into a set of clauses if you want. And that would be needed as we are dealing with tree-like resolution, which only operates on set of clauses. But that is pretty obvious. And if I asked you to come up with a translation, you will come up precisely with that one. Then it makes sense to consider only first-order sentences that have no finite models, because when we translate them into propositional formulae, we want to get contradictions. Now, for such translations, we have only two cases. Either all the translations have tree-like refutations of size polynomial in n, where n is the size of the finite model, and that happens for every finite model, for every n, or they require tree-like resolution refutations of size fully exponential in n, 2 to the constant times n. And hence the name complexity gap. There is nothing between polynomial and fully exponential. You can never have things like 2 to the polylog n or exponential in square root of n, nothing. It's either very easy or very hard. And moreover, The criterion that separates the two is very natural. The easy ones are the ones that have no models at all, neither finite nor infinite. And in fact, those are precisely the contradictions in first-order logic. So they have refutations in first-order logic, and you can, well, intuitively you can translate such refutations into polynomial size refutations in tree-like propositional resolution. Some work is needed, but it's not difficult, and it could be done. For the hard case and the examples that I mentioned, the pigeonhole principle and the least number principle that fail in all finite structures but have an infinite model, well, again, it's quite intuitive that you can use the infinite model as an adversary argument. And I should have said that if you don't know what tree-like resolution is, think of it as a Boolean decision tree that queries the propositional variables and stops as soon as a contradiction to one of the original clauses is found. And so you can use the existence or the infinite model to fool such a tree, to force a big balanced subtree, and that would give you the exponential lower bound. Now, what has this to do with parameterization? We look at all this from a parameterized point of view. Remember, now we have a tree-like resolution plus the additional restriction that we don't allow assignments of more than k propositional variables set to true. It makes sense to look only at the hard case, the second case, because the first one is easy no matter if you parameterized or not. And we did that, and perhaps not surprisingly, the classically hard case splits into two, one of which is fixed parameter bounded, and the other one which isn't. Well, now we, of course, only look at first-order formulae that fail in all finite structures, but have some infinite model. It splits into easy and hard case, and easy is, as you may imagine, polynomial in n times exponential in k. The hard one is a lower bound of n to the polynomial in k. Now, the criterion that separates the two is whether in every infinite model of the first-order formula, the induced hypergraph has a finite dominating set or not. So if it so happens that in every infinite model of the original first-order formula, the induced hypergraph has a finite dominating set, then it is easy. Otherwise, it is hard. Just to give you an idea as to what I call a finite dominating set is I look at the elements of the universe, and the hyperedges of the hypergraph are the relations. And so a finite dominating set is a finite set of elements, so that everyone is either dominated by some of those or is dominated by itself. There may be a unary relation, or even with binary and other relations, it could be the case that some of the elements are dominated by itself. if you think about it. So that is what is finite dominating set. And it is intuitively clear as to why this is easy. If you had a finite dominating set, a Boolean decision tree can witness those green elements that constitute the dominating set in polynomial time, polynomial size, n to the number of elements. And once that's been done, for everyone else, the decision tree would make all possible queries that involve that guy and the guys within the dominating set. And that would take some constant number of queries that transforms into a constant branching factor. So if you repeated that at most k times, you would get, well, at least k variables that have been set to true that would close the branch. So the product of the two gives you the FPT bound. This was just to give you an idea as to how that worked. And well, that's what we did. Embarrassingly enough, we set as an important open question proving a parameterized lower bound for the pigeonhole principle. You will see in a minute why this was embarrassing. So we first observed that under the embedded parameterization, the pigeonhole principle was easy. It is not difficult. It's essentially because the pigeonhole principle from n plus 1 to n transforms into the pigeonhole principle from n plus 1 to k, and that's easy. We said we didn't know how to do it under the naive relativization parameterization. Of course, from the complexity gap theorem, it follows that it is hard for tree-like resolution. If you think of an obvious infinite structure where the pigeonhole principle holds, you realize that it hasn't got a finite dominating set. But we asked if it was easy for a resolution or not. And in fact, some other people, most of whom are in the audience, figured it out pretty quickly that it wasn't easy. In fact, they proved the lower bound, and the proof is quite easy. So that's why I was kind of embarrassed that we put it as an open question, and then someone comes up with an easy proof. I wouldn't say it's easy to find, but once you found it, you realize it's quite easy. It's quite nice, in fact. So what happens, I won't go into details and calculations, but it's a reduction from the parameterized pigeonhole principle into the ordinary pigeonhole principle. And what they figured out is that one could pick parameterized refutation. That is a refutation that uses some of the original clauses over here. Well, in fact, all the original clauses say over here, plus some parameterized clauses, some of the extra clauses. But if the refutation used very few of the extra clauses, and very few in this context meant fewer than n to the, say, k over 5, what they did is they hit the refutation by a random partial assignment that only left n plus 1 pigeons free and n holes. And then they argued, and that is the heart of the argument, but once you figured out that it could be done this way, it's not difficult to actually estimate the probabilities and the numbers. They figured out that with high probability, such a random partial assignment would kill all the extra clauses. Killing them in this context means they will evaluate to true. And so for if that happens with reasonably good probability, that means then there is a specific assignment of n minus square root of n pigeons to that many holes that kills all the extra clauses. And what you are left then is just an ordinary non-parameterized pigeonhole principle from square root of n plus 1 to square root of n. And it is known that this that version of the pigeonhole principle is in fact hard for bounded depth Frege. So they proved straight away that the parameterized pigeonhole principle was hard for bounded depth Frege, which is, well, I'd say it's the strongest result in the area up to date. Well, of course, one can argue that the proof is so nice and easy only due to the fact that we use those extra clauses. And one can argue that in bounded depth Frege, you can replace all the extra clauses by a single bounded depth formula, which says that we restrict the assignments only to those of weight k or smaller. And one can indeed check that such a bounded depth formula exists, and it's of size 2 to the k polynomial in n. So I don't know what happens with the pigeonhole principle under that parameterization, but I suspect it would be easy. So if you have n inputs and you want to count but only up to k by AC0 circuits, that is doable, I believe, in 2 to the k or even smaller times a polynomial in n, and that should give you short proofs. So I believe it's still an open question and a difficult one to find a lower bound for bounded depth Frege in the parameterized setting where the parameterization is done in more sensible way, not in that naive way.
So maybe you can also just pointing out that the fact that the random restriction there is working is due particular to the fact that we are considering pigeonhole principle, and then few ones are killing some process. So for other principle is not working, the reduction to the usual lower bounds for the pigeonhole principle to just usual systems. It's for the particular form of the pigeonhole principle that is working, because you can kill the parameterized clauses with
yeah, well, it is true that that reduction, that random restriction is very specific to the pigeonhole principle. That's fine, but the important thing is that it is also specific to the silly parameterization that we introduced. And we did that because, I mean, in resolution or tree-like resolution, you can deal only with clauses, so there is no other way. But
probably you will mention later that if you consider bounded with formulas, then you will have just short parameterized repetition.
That's right. Although that might be one of the results that I don't like, so I might not mention it.
Okay, good. Good to know then.
well, anyway. So, well, this same people, except for Sasha-Zborov, they actually found a contradiction in which parameterization comes naturally. You know, everything that I considered up to now, it was this generic parameterization by the weight of an assignment. And a priori, it's not clear why one should consider it. I mean, what does it mean? Why is it? Why does it make sense? Of course, one can argue that it makes sense because of the W hierarchy and the generic W2 hard problem, complete problem, but that's the only reason. In this setting here, what does it mean that you allow at most k tuples in all relations altogether? It makes no sense. We produced this result only because we could. Well, it is true. Because that was the only thing we could prove, and we could link it to something that was known. So it was very important to find some kind of contradiction or many contradictions in which the parameterization comes naturally. And well, those contradictions found by Olaf Beiersdorf, Nicola Gallesi, and Massimo Loria, they are the k-click in a random graph. If you pick the usual Erdős-Renyi model of a random graph, n vertices, every edge is chosen with certain probability independent from all the other edges. If you pick the probability right, you get a graph on n vertices that contains no click of size k. Now you can quite easily encode the fact that it does contain a click of size k by simply mapping a set of size k into the graph surjectively, and every two that you map to the vertices of the graph here, you say there must be an edge between the images. That's what it means to map a set of size k into a click. So that is a contradiction if you chose the edge probability carefully, and then you can ask how hard it is to refute that contradiction, and it turns out that it is hard to refute in tree-like resolution. Well, the proof is very nice, and Olaf, I believe, is talking about it immediately after me, so I won't say anything more. Well, an obvious conjecture or an open question is whether you can extend this result to resolution or even bounded depth Frege. And the reason I believe you could extend it is because this k-click is not FPT bounded. It is complete for W2 or W1, I don't quite remember, but in any case it's not FPT bounded. So I wouldn't expect that you could refute the existence of click on all instances by even a powerful proof system. So at the moment I'd say that this is the most prominent candidate for showing parameterized lower bounds for strong proof systems.
So in this theorem, the graph can be any, or it has to be the random graph? Any
The
graph
random graph.
which doesn't have a k-clique, or the random graph?
Well, they proved it for the random graph with that specific edge probability up there. And so, if you look at the proof in their argument, it's quite natural and nice for the random graph. You could come up, I think, and I think the paper contained an example of a structured graph, but I'm not quite sure. But so those examples, they are easy for stronger proof systems simply because you could see the structure and you could realize that there is no k-clique straight away. Perhaps I should say that this problem, finding a k-clique in a random graph on n vertices, it has received, well, there has been progress. For instance, there have been recently or not so recently, two lower bounds for AC0 circuits and for monotone circuits. So proving lower bounds in proof complexity is a natural step. And an important one, I think. In particular, if one can do it for resolution. Have you got the result for resolution?
No.
Okay, so it's still an open question.
So, but I didn't get exactly your conjecture is that it's hard for resolution.
Yeah. So this is something technical, but as I see I have time, I will bore you with that as well. So it's something which is, I believe, somewhat easier than proving lower bound for the k-clique, but is of similar nature. In that, I map a set of size k plus 1 surjectively to a set of size n, and then I map that into a set of size k. So I have, well, if you think about it, it's a pigeonhole principle from k plus 1 to k, but I put in the middle some big, huge set of size n. So I map surjectively that into the middle, and then everything in everyone which is an image of someone here, I map surjectively into k. So if you compose these two maps, you get the pigeonhole principle from k plus 1 to k. But you can compose them only in something called resolution 2, which is resolution that allows not only single literals, but small conjunctions of size 2. You can't do that in resolution, and I believe that one over there is hard for resolution. I didn't put it down. Well, I did put it down as a conjecture, but I hope no one can come up with the proof straight away. So one last natural parameterization would be achieved if you look at first order sentences again, which fail in all finite models as usual, but have some infinite model. So now these sentences we figured out, as Søren Ries proved, they are hard for tree-like resolution. In general, they aren't hard for resolution. You can pick the least number principle which satisfies this, but it is easy for resolution. However, if you relativize those sentences in the obvious way, instead of saying the sentence has a model of size n, you say the sentence has a model over some subset of a set of size n. Well, then everything becomes hard for resolution, simply because resolution cannot count. It is able, for instance, resolution can prove that a total order has the smallest element over the entire universe, but if you insist that it proves that a total order has the smallest element in every possible subset, resolution cannot do better than counting over all these subsets, which takes exponential time. Well, so if you did that, but you restricted the size of the potential subsets to be at most k, you get something which is parameterized and more or less naturally by k. Then I would expect that this parameterized contradiction is hard for resolution. But I have no proof, and I haven't actually tried really. So the remark down there is that old result by Søren Ries and myself, where we proved the lower bound for resolution in the classical setting, where the size of the subset is not bounded in any way. So this is another well, candidate for lower bounds in parameterized resolution. And that's it.
Thank you very much. Are there some questions, please? Yeah.
Where does bounded width resolution fit into this?
Bounded depth Frege, you mean?
Bounded width.
Bounded width.
Bounded width refutation. So now there is a claim by Martin Boy that this is going to be, does there exist a bounded width refutation? This is X time complete. This should give us an example of something that is not fixed parameter tractor.
Well, I've never actually thought about bounded width resolution. It sits in between tree-like resolution and resolution, and in fact it is the same as tree-like resolution in which we allow, instead of literals, conjunctions of size up to the width. Yeah,
No, I don't think so.
it's a result by many people, like Nicola Gallese and someone else.
Right? But the clauses, you don't want the clauses to be more than the
No,
width.
you want all the proof
width.
of bounded width, not on right.
All the clauses, not the
Yeah.
initial thing. All the clauses.
Yeah, that I understand, but isn't it so res star W
Oh, yeah.
would be tree-like resolution where you allow,
Yeah, you're right.
instead of literals, conjunctions of size up to W.
I don't see it. I don't know why. I don't see it. Maybe it's true, but I don't see why.
Well, I didn't see it either.
Oh,
I
this
had a
side
glance
is
at the
K.
paper and I still didn't see it, but I believed it, so I think it is true.
But the point is that that we know it's a hard problem. I mean, so you get the number of clauses, right? The bound, the natural bound of this is going to be indeed of n to the k.
Well, you have to be a bit careful. What exactly is x time complete? Given
Given a formula and
given, say, a contradiction, to find if there is a refutation of bounded width. Yeah.
k is the part of the problem.
Mhm.
Okay.
But that's a bit different problem. Yeah. So
But now you can ask, is there a proof of this, right? So the obvious proof is the refutation itself, which is of size n to the k. So that you could ask, is there the same kind of question you can ask? Is there a refutation of somehow of this?
Well,
And the question is, there is going to be a proof of size f to the k times n.
what you are suggesting goes more into the direction of this automatizability results, you know.
I'm trying to see how it fits in your framework, and I think you could fit in your framework, and the answer should be you should be able to prove that it's not FPT in that sense.
Well, we could discuss it, but I think what you're suggesting goes into a different direction.
Maybe.
So what we are looking for here is hard instances for certain proof systems. And you are looking at something else, you know, given any instance, tell me if it is refutable.
No, I'll give you a parameter. It's kind of seems that it's a different type of parameter. You're looking at the number of. It's a different parameterization. It seems to be. It's a parameterization that's not on the truth assignment, but the parameterization of the structure of the proof.
Well,
the equation is like a promise problem. They are simply given things which do have refutation, which I want to estimate the length. While in your case, it doesn't have to be refutable at all.
well, we share an office anyway, so we can discuss it.
So you share office and you talk with yourself only in the lecture.
But well, I don't know. So there has been a recent paper discussing different kind of parameterizations. Well, I think it's one of the things that I don't like, so I didn't mention it.
Okay, we don't want to know the authors. So, is there some other question, please? So let's thank the speaker again.